So the next lecture will be given by Chris Moore, and as Patrick explained to you earlier about how we somehow build the program of this tool around the connection between what certain class of methods can do in physics of disordered systems and in other fields somehow related to computer science, even much broader than computer science. So this connection somehow have a long history that, some parts of it, important parts of it started in Europe by works of people like Parisi and Mézard. But I would say that on this side of the Atlantic, the main person running this connection would be Chris Moore. So that's the way to.
Thank you.
That's the right person to give this introductory lecture on this. When we had this computer science part.
Oh, thank you. Well, being an import-export agent is great because you can explain things to Group A that Group B thinks is trivial and vice versa. So thank you very much to Lenka and the other organizers for inviting me. So I hope to introduce you to some things this week. One thing I want to tell you is that computer science is not the science of computers. So we had a great talk by Christos Papadimitriou, who is a leading theoretical computer scientist in Santa Fe recently, and he said, computer scientists spent so much time thinking about computers that they made the mistake of naming their field after them. So, computer science is, I would argue it's like statistical physics in that it is the study of the structure of different problems, in particular, different search and optimization problems. And it's the study of the fundamental mathematical structure of these problems and how those structures make it possible for certain algorithms to work, certain classes of algorithms, and how in many cases the structure implies or strongly suggests that there are no efficient algorithms for these problems. So I'm going to start today with some basics about computational complexity with a few physics-inspired examples. And you've probably heard, for instance, that finding the ground state of a spin glass is NP-complete, whatever the heck that means. So by the time you walk out of here, you'll know exactly what that means, if you don't already. How many people could actually tell a friend what that means? On a napkin in a bar. Good. Okay. All right. Let's see. So computer science talks about these complexity classes. So a class is a class of problems, and a problem is an infinite class of examples. Okay, so for instance, finding the ground state of a spin glass, given its topological structure and the set of all the couplings on all the edges, that general thing is called a problem. And that problem may or may not belong to different complexity classes depending on how hard it is to solve in general. So let me start out by mentioning two problems that are superficially quite similar. And I'm sure you've already heard of these, but all right. So one of them is the question of, can you draw this figure without lifting your pencil off the page and without covering any edge twice? Okay, you may have had this in a child's puzzle book. You might still have it in a child's puzzle book. But you try to do this, and one way to do this would be by backtracking search, right? I could do that and then that, and oh, but now I'm stuck here because I already did those two edges. Okay, maybe when I got here I should have gone that way instead, but now I think I skipped an edge somewhere. So you could do this by exhaustive search. The only annoying thing about exhaustive search is that if you had n vertices here and roughly 2 ways to exit each one after entering it, then that exhaustive search would take you about 2 to the n time. And that would be bad if n was 1,000,000 or something. Luckily, you don't need to do exhaustive search here. All you need to do is, let's see, can we do this problem? I guess we can do this problem. If we do this, and then that, and then that, good. So there, we did that problem. Okay. Okay, I did not do that by exhaustive search. But now, suppose that we make the problem a little bit different by adding another edge there. Okay, now can we still do it? Okay. So you may recognize this sort of problem from the classic bridges of Königsberg problem, where long, long ago, before more bridges were built and then some of them were bombed, there was the town of Königsberg and the river Pregel, and there are 2 islands, and there are a bunch of bridges between the islands. And so if we abstract this into a graph, and indeed this was the graph that began graph theory in the hands of Leonhard Euler, then the question is, can you spend an afternoon touring every bridge, crossing each one exactly once? And that's the same as drawing this figure without lifting our pencil from the page. So what Euler said is, you don't need to do an exhaustive search. Okay? All you need to do is check to see whether the degree, the number of edges coming out of each vertex, is odd or even. Because every time you enter a vertex, you have to leave by a different vertex. And that means that, every time you enter a vertex, you have to leave by a different edge than you came in on. And that means the edges have to come in pairs. And so that means that every vertex has to have an even number of edges, except maybe for wherever you begin and end the tour. Okay? So as soon as we check that this has 3, and this is 5, and this is 3, and this is 3, and that's what I made. I changed these from 4 to 5 when I added that extra edge. We now know that no Eulerian tour, as we call these tours in honor of Euler, no Eulerian tour is possible. There's no need to search. So pause for a moment here and recognize that something profound has happened. The number of potential tours of a graph with n vertices is exponentially large. And asking you if any of those manage to cross each edge exactly once is a potentially hard problem. And yet Euler has achieved a mathematical insight into the structure of this problem that avoids any need for that search. Okay? So it's a big deal.
Does the converse hold if they're all even? Can you do it?
I leave it to you to prove by induction that if you have a connected graph where every vertex has even degree, then there is a tour which starts and ends at the same point. And if exactly 2 vertices have odd degree, there is a tour which starts at one and ends at the other. Okay. Yes?
So this, even the first odd number that tells you it's possible, but it doesn't tell you how.
It's true, it doesn't tell you how. It doesn't tell you how. Although if that's true, it's not too hard to find one.
You don't need
you're right, that's a non-trivial question. I think it's the same question as his. So there is a polynomial time algorithm, there I said it, for finding a path if indeed one exists, and one exists if all of the degrees are even. Okay, yes?
So on the first picture here, do you have?
On the first picture, yes, this had degree 3, this had degree 3. Before I added that to make life harder, this had degree 2, 4, and 4, and so indeed there is a path which begins and ends at the 2 vertices of degree 3.
Oh,
Okay.
so 2 basically nodes with odd degrees are allowed.
Exactly. As long as those are the endpoints of your path. Okay, good. All right. So now this shows that the question, at least the yes or no question of whether an Eulerian path exists, whether it is possible to tour a graph and cover each edge exactly once, where, again, what I mean here is I want to be able to challenge you by handing you any graph, and then I want you to be able to answer for that graph that yes or no question. Or better yet, the search problem of actually finding the path. So we just proved that that problem, which we can call Eulerian path, is in a class called P. P stands for polynomial. And what it means is that the total amount of computation you need to solve this problem grows only as some constant power of the size of the example, computer scientists sometimes say the instance, that we're trying to solve. Now, what do we mean by the size? Well, pedantically, it's the description length in bits. So it's the length of the email I need to send you if I want to tell you, can you please check to see whether this graph has an Eulerian path? But for problems on graphs, you might as well think of it as the number of vertices, or the number, or the number of edges or something. And we really don't mind if it's n or n squared, and so I really don't care what format you give me the graph in, because any reasonable format will only differ from any other reasonable format by a polynomial. If it's sparse, fine, you can make it smaller, but that's only n versus n squared, and so on. Okay? So does everybody understand what we've shown here about the Eulerian path problem? Okay, good. I already know from the first talk that you're an active group who will not hesitate to interrupt with questions. So, all right. Now, let me show you another problem which is superficially quite similar. So in this problem, the goal is to visit, not to cross each edge once, but to visit each vertex once. Again, I want to know this for general graphs, but here I've drawn one of my favorite graphs. And this is also the graph which Lord Hamilton, the same one as with Hamiltonians of physics and quaternions, unsuccessfully marketed a game where one player chooses the first 5 steps on this graph, and the other player has to try to complete them. And again, the goal now is to visit each vertex exactly once. And I think we can do this. If I recall correctly, you sort of have to loop around, and I'm not, oh, no, I got stuck now. Okay, gee, it's not obvious. Okay, so in honor of Hamilton, we call these paths Hamiltonian paths, or Hamiltonian tours. And a kind of weighted version of this, or minimization version of this, is the classic traveling salesperson problem, where I have a bunch of cities and I need to visit each city exactly once, and every time I go from one city to another, there's some cost I have to pay in airfare or distance or something, and I want to know, can I visit them all within a certain budget? It's a slightly different version of the problem. So the wonderful thing is that even though this problem sounds a lot like the first problem, we think it's much harder. In other words, we do not know of any simple local mathematical property analogous to, oh, just check whether the degrees are odd or even, that let us answer this question. We think, essentially, that you need to do the search problem here. Okay? Which, could be bad news. Again, if every time I enter someplace I have 2 ways to go, then I'm going to have a tree of 2 to the n possible tours. And as we'll see, it's not just that no one has thought of something like this yet. It's that we have very good reasons for believing that there is no shortcut. Okay? And indeed, if it turns out that there is a shortcut, then many other problems instantly become much easier than we think. Okay? Good. Yes?
So this is this specific to a particular, this is a random collection of cities and connections? Or
That's a very good question. And I was going to say that at the end, but let's say it now. It's not a random collection. So computer scientists live in a very grim world, okay? A very strict world. If a computer scientist says, I have an algorithm which solves, say, the Hamiltonian path problem, what she means is that if anyone gives her any graph, that she can solve the problem on that graph. And if she says, my algorithm runs in n cubed time, where n is the number of vertices, she's making that claim about all graphs, okay? But that also means that she's making that claim about the worst possible graphs. So it means that if a clever adversary, here's this nice word, if a clever adversary makes up the trickiest possible example of this problem, her algorithm has to work. Now, of course, that's very different from what, this week, this month is about for the most part, right? So these are not random examples. There's no sense in which they're typical examples. They are worst case examples. So we'll talk about this more later, but theoretical computer science, for the most part, deals with the worst case complexity of problems. And okay, all right, let's talk about this now instead of at the end. So I think this is because this field was kind of born in World War II, right? It was born out of cryptography. And things like Alan Turing and the Allies trying to break the Nazi Enigma code. And in cryptography, there really is an adversary trying to break your codes and trying to come up with codes that you can't break. But of course, physics, we don't deal in these horrific adversarial worlds. We say, hey, nature, what's the connection between mass energy and the curvature of space-time? And nature says, the simplest possible connection. We say, oh, thank you, that's so beautiful. So, physicists live in a much more benevolent world where the answer is usually the simplest possible. Now, I also deal with sociologists and biologists, and there it's really not clear whether that's true.
Just as a follow-up, what is it? How do you measure work? Like without knowing the answer, without having.
It can be hard to tell what the worst case complexity is, right? Yeah. Let's see. Let's define the intrinsic complexity as a problem, of a problem, as the minimum running time over all algorithms, but defining the running time as the maximum over all examples of a given size. Okay? Too many quantifiers? Did you get that? So if you define an algorithm as one which works on every example, the intrinsic complexity is the running time of the best possible algorithm that always works. Now, to get an upper bound on that, all I have to do is show you an algorithm and prove to you that it works. And like many things in mathematics, proving it to you that it works is often the easier part, right? Coming up with the cleverness of the algorithm is often the most of the work. So upper bounds on complexity are easy to obtain. A lower bound, that's much less clear, right? So how would I prove to you that there's no way to avoid exponential time here? Or suppose I claimed that some problem required at least n to the 7th running time. How would I prove that to you? I would somehow have to reason about all possible algorithms. And the one that you think intuitively is the best possible might not be the best possible. Okay, we have been surprised before where problems suddenly turn out to be much easier than we thought. So proving lower bounds on complexity is quite tricky. So that's partly what this will be about. All right, so This problem does live in another class called NP. The N does not stand for non. Notice that it is a superset of P, not the complement of P. It stands for non-deterministic polynomial time, but that's for historical reasons that we should leave in history. What it really means is that a problem is in NP if you can check solutions, okay? So if a friend hands you a solution after thinking about it for a long time, or God tells you one in a dream, or you just get lucky, you can at least check that it works. That's certainly true here. It might be hard to tell whether a solution exists. It might be hard to find one, even if you know it exists. But if you are looking at one, you can check that, yes, it does visit every vertex exactly once. Okay, so NP is the set of problems where solutions can be checked. P is the set of problems for which solutions can be found efficiently. Yes.
So for the weighted traveling salesman problem, does that include most efficient?
Wow, these are great questions. Okay, you're absolutely right. So finding a minimization problem, an optimization problem, is typically not in NP, strictly speaking, because of exactly what you said. If I show you a tour and I say this is the shortest possible tour, how can you check that? For that matter, how can I give you any simple proof that it's the shortest possible that you could check easily? That's not clear, because I would have to make some claim about all the other ones being worse, and that might take some exponential time to check them all. On the other hand, the yes or no version of traveling salesman, like I claim that it's possible to visit all the cities with less than 10,000 miles of travel, you say, can you please prove that claim to me? I say, here's how to do it. You check it and say, oh yes, I see. Okay. So we often, in order to fit things in NP, we often switch from optimization problems to decision problems. Can you achieve such and such or better? Such as, does this spin glass have, is its ground state energy less than or equal to such and such a thing? And I can prove that to you simply by showing you such a state. Okay. All right. Good. Okay. So let me say something now about landscapes, because the metaphor of the landscape, I guess at some point here I need to stop erasing and start moving. Okay, all right, I'll do that next. The metaphor of the landscape seems to play an important role in computer science as well as in physics, and by the way, also in ecology and so on, and where people talk about fitness landscapes and so on, except they're upside down. For some reason, in ecology, things want to go up. I don't know why. So here is a problem that you should know about. The problem is called minimum spanning tree. So this is a nice problem. What we have is a weighted graph, or in the original version, which goes back to the 1920s, we have a set of cities with distances between them, and we want to connect these with a network with the smallest possible total length of all the edges. And originally this came up in the subject of building an electric power network for the region of Bohemia. Now, if you really want to just barely connect to everybody, then there's no need for loops. So you're going to want to have a tree. Of course, you would not actually want your electric power network to be a tree, but let's not worry about failures of our electric power network at the moment. Okay. So there is one class of algorithms called greedy algorithms, which in physics we would call a zero temperature quench. So how does it work? Well, you at each step do in the short term what seems best right now. which of course is usually a terrible idea, but for some problems it works. So what we do is we take the pair of cities that have the shortest edge between them and connect them, and then keep doing that. Maybe this is the shortest, and then that one, and then, I don't know, maybe this is the shortest pair, and then maybe that's the shortest pair, and then maybe this one, and then maybe that one, and let's say this is the shortest, but if it completes a cycle, we skip it, because those are already connected, and then, I don't know, maybe there. Okay. So I just described an algorithm that tries to find a spanning tree. Does it find the best one? I mean, normally a zero temperature quench would not normally find the ground state. So why should we believe that this greedy algorithm finds the shortest possible spanning tree? Well, in fact, it does, and I won't belabor it too much, but it's a simple proof by contradiction. Suppose, by contradiction, that the minimum spanning tree contains this edge, which is not the edge that the algorithm wanted to add. Okay? Well, now imagine adding that one too. We now have something which is a spanning tree plus a loop. And if we delete one of the edges on this loop, we'll still have a spanning tree. So if but why would you delete this one? Sorry, why would you delete this one if it's shorter than that one? So you should delete this one after all. Okay? All right. That was not quite at the level of a math course, but I think, that's basically how the proof works. Good. So for the minimum spanning tree problem, a greedy algorithm works just fine. And one way to view this is that the landscape of spanning trees, or actually maybe partial spanning trees, looks like that. So there's another closely related algorithm where you start with any spanning tree you want, and then you do moves where you complete a loop and then take away the longest edge in the loop. Either of these things work, so basically, gradient descent or just a quench or greed works just fine. It's a simple landscape. There's no danger of getting stuck in a local optimum, which is not the global optimum. Yes? Yes. If you want, you could have a complete graph and then have weights on the edges. But were you asking about a maximum spanning tree? That works too. But yes, that will also work. Yes. Yeah. You can nibble away from a complete graph, or you can build up a tree. Yes. Yeah. Okay, good. On the other hand, if we look at the traveling salesman problem, where we have a series of cities that we need to visit, what might a greedy algorithm do? It might say, go to the nearest city that you haven't visited before, and then you might do this, and then you might say, oh, dang, we forgot that one. And then you have to pay a big cost to go back there. And of course, what you should have done instead of being greedy is thinking ahead a little bit for once in your life and do that instead. And then you would have had a shorter total path. Okay? This is kind of interesting because the traveling salesman problem is a lot like the minimum spanning tree problem, because paths are also trees. They have no loops. It's just that paths are trees that are not allowed to branch. So when we add the no branching constraint to the minimum spanning tree problem and demand a path, suddenly the landscape goes from being simple to being very bumpy. very glassy, with lots of local optima that you can get stuck in. And now it becomes really unclear how to solve this problem efficiently. All right. I want to give you one example of where, yes? Not as glassy as the glassiest in what? I don't know.
I do.
Okay, well then you shouldn't have said maybe. Okay, not as glassy, but kind of glassy. Glassy enough to make it unclear what to do. All right. Now, there's another problem I want to show you, which, sort of one more thing from your first semester computer science class. And I want to show it to you for two reasons. One is that this notion of a landscape is actually not always totally well defined. So in the max flow problem, we have a directed graph. And in this problem, there are two special vertices, our source and our destination. And each edge of the graph has a capacity, which is the amount of flow that can travel along it, although I prefer to think of this as seats on airplanes or trains that I can put my students on to get from Santa Fe to Turin. Good. I was about to say Tucson. Thank you for, Turin's much nicer. No offense to any Arizonans. Anyway, so the question is, what's the maximum number of students we can get from here to there along these things where these are the number of available seats? Now, there is one kind of greedy algorithm here which does not work. So there used to be these people called travel agents that you would call on the phone, and then they would arrange things for you. So anyway, the way this worked is that the travel agent might say, yes, I found one itinerary for your students there that one student can get that way. We just used up one of the two open seats on each of those edges. And then that one, and then the travel agent could say, but I just have a special deal. There's one seat left here, there's one seat left here, and there's also this nice scenic route, so we'll do that. Okay, so that's one way that a greedy algorithm might go. The only problem is that now we're stuck. We've only gotten 3 students to Turin. We've used up both of these seats. This only goes one way, and now there's no way to get anyone else there. And of course, what we should have done is send 2 that way, and ignored this scenic route completely, because, why waste the scenery on mere graduate students anyway? Sorry, just trying to entertain you. So now there is a slightly fancier greedy algorithm. As you know from reading Feynman, positrons are electrons moving backwards in time. And so all we need is to allow the creation and annihilation of student-antistudent pairs. And if we do that, we can add this path, which creates, here is a student, here they annihilate an anti-student moving backwards in time, and here is another student, and this virtual pair goes away. And now we've gotten 4 students there. Okay, so for some reason this student-anti-student metaphor does not appear in the computer science textbooks. But now what we've done is we slightly expanded the set of moves we're allowed to do by going along these backwards edges. And I will not prove it to you, but it can be proved that when you do that, this problem then looks like that. Now the greedy algorithm works. There's no danger of being stuck in local optima. And so I bring this up to point out that when you describe the landscape of a problem, I really hope I don't spill that. One of the things you need to do is define which states are neighbors of which other states. And in physics, we usually think of that as single spin flips or something. But in this case, slightly expanding that notion of neighborhood takes us from a rugged, possibly slightly glassy landscape to a nice, smooth one. All right. That's one reason I wanted to tell you about that. The other reason I wanted to tell you about the max flow problem is to introduce an important concept called reductions. A reduction is a very poorly named concept. If I could go back in time, I would call it a translation. Here's the idea. Let A be a problem, and again, not just a single example, but a whole class of problems, like the max flow problem in general, say. And let B be another problem, and suppose it were possible to translate any example of problem A into an example of problem B. And suppose further that this translation process was pretty easy. Okay, in particular that it only requires polynomial time. And I'll show you an example in a moment to make this more concrete. Well, if I can translate from A to B, that means that if B is easy, so is A. Because I have some marvelous fast algorithm for B. This now lets me solve A. Just translate from your example of A into an example of B, and then I use my fast algorithm there. Yes? Well, that maybe that's one thing it means. It means that there's a polynomial time algorithm for it. Yes. That seems to be related with things like smooth landscapes, but in this example, I'm trying to argue that this notion of a landscape is not always totally well defined. So, yeah. I mean, after all, like think about. So we'll talk later about constraint satisfaction problems. Think about XOR sat. If you have ever thought about XOR sat, if you don't know what I mean, think about Gaussian elimination. Okay, so finding the eigenvalues of a matrix can be done in polynomial time using Gaussian elimination. What is the landscape there? Right? What are the moves? Well, you're subtracting multiples of rows from other rows. Okay. But, what if you came up with some totally different algorithm with different moves? So the landscape is not always a well-defined property of the problem itself. It's more like the problem and the moves that you've thought of so far to try to go from one possible solution to another. Yeah, okay. Okay, so does everybody understand this? If I can translate from A to B, if I can solve B quickly, I can also solve A quickly. This also means, by the way, that if I somehow knew that A is hard, that would imply that B is also hard. Yes?
Translating means mapping one to another.
Yes. So what it means that if I have an example of A, I can translate that quickly to an example of B. And for yes or no questions, let's say that this means that an example such that the answer to the yes or no question is the same. Okay? So it's like, and by the way, if your translation itself is taking so much computation that you're actually answering the question, that's cheating. Okay? So you're at the embassy cocktail party. You're an interpreter. The general of whatever comes up to you and says, to your general, would you please move your troops back from the border? You're not supposed to say, yes, I'd be happy to do that. You're supposed to dutifully translate the question so that your general can answer it. Yes?
Does this mean that you can translate back from B to A?
Not necessarily. Not necessarily. B might be a more general question than A. Okay? So there might be examples that don't, it might be that A is a sort of subset of B, or could be translated to a subset of B. Yes?
How do you know the translation is necessary?
Let me give you an example. So maybe this is still a bit too abstract. here is another question, another problem for you, called bipartite matching. Bipartite matching. Okay. So in this problem, you are running a dating service. It's a dating service for a very unusual subpopulation that are only interested in monogamous heterosexual relationships. So it's, I don't know, you've gone back to the 1950s somehow, but you brought a computer with you. I'm not sure what the story is here. And the question is, given a bipartite graph which tells you which couples are compatible, your goal is to match them all up so that everybody has a partner. And for some reason, the men are always on the left and the women are always on the right in this story. And you can see in this case, we better do that because that's the only choice. And then I guess, okay. So there is a perfect matching. So the problem here is now, given this bipartite graph, does a perfect matching exist? And notice once again, conceivably, if there are n people here and n people there, there could be n factorial potential matching. So it's not totally obvious how to do this problem quickly. Okay? Yes?
Once you match, there's only one part.
That was one of their unusual properties, yes. Yeah. So each one wants a unique partner on the other side of the graph. Okay, so now it's not obvious how to solve this quickly, but I'm going to show you how to solve it quickly, given what I've told you so far. Add a vertex over here and call it S, and add a vertex over here and call it T, and make all of these edges, sorry, not there, and put a capacity of 1 on every edge. And now the question of, is there a perfect matching, is the same as the question of, is there a flow which actually gets n units of flow or n people from S to T. Okay, so if you believe me, I didn't really prove it to you, but if you believe me that max flow can be solved in polynomial time, I have now proved to you that bipartite matching can be solved in polynomial time. Now, I wanted to show you this example because in this case, it's clear that this reduction or translation is very simple. We just added these things. We sort of didn't do any non-trivial processing. Typically, it involves, sort of replacing nodes or edges with extremely technical things that we call gadgets. A gadget might be a little group of nodes or edges, or something like that. Okay, so it typically involves just some local rewriting of the problem. That's what these reductions are. That's what these translations usually are. Okay, now.
Can you say here A is basically B because there's.
I know here there's almost nothing. There's almost no space in between. But yeah, but did you think of that before I said it? Okay, there you go.
Also, it's possible to have more than one solution, right?
Oh, absolutely. Yes. And here notice that we keep just asking this question, is there a solution or not? But in general, we might want to actually find one. We might want to count how many there are. But that actually, counting how many there are actually belongs to a higher level complexity class, which I'll tell you about if I have time. So that's more like computing a partition function or something, summing over a potentially exponential number of states. Okay.
So there's NP means you can check a polynomial time.
Yes.
There's class where you can't do that.
Suppose, Merlin comes to Arthur, and Merlin says to Arthur, hey, Arthur, there's this cool game from Persia called chess, and they play it for a while. And then Merlin says to Arthur, by the way, white has a winning strategy. And Arthur says, I am a poor polynomial time mortal. Can you prove to me that white has a winning strategy? And Merlin, with his godlike levels of computation, knows that white is a winning strategy, but doesn't know how he can prove that to his poor mortal friend. Just playing over and over again isn't a proof. So that's an example of a problem which is not apparently in NP. Especially, we should be a little careful here. Merlin could just hand Arthur a book the size of the Milky Way, which contains every possible game. But so to really make it outside NP, we need to generalize this to n by n boards with extra pieces so that it's really an infinite class of possible games. But that's an example of something where it's not clear how to check it. But let me give you a simpler example. Suppose I give you a graph and I claim there is no Hamiltonian path. We do not know how to check that in polynomial time. Or I give you a spin glass and I tell you the ground state energy is greater than something. How do I, even if I have lots of computational power, how do I give you a proof of that you can check? Okay. All right. So now that you know this notion of reduction, and you know how easy it usually is, and by the way, this is often written like this, like a less than or equal to, because it does mean, modulo the translation process, which is easy, it does mean that B is at least as hard as A, and that A is at most as hard as B. Okay. Now, let me throw the following crazy definition at you, which was invented simultaneously by several people in 1972. We say B is NP-complete if we can reduce, we can translate, reduce is what the computer scientists say, but it's a stupid word because B is often a bigger, more general problem than A. Anyway, okay. If we can translate from A to B for any problem A in NP. Okay? What does this mean? It means that for any problem, let's say yes or no question, where if the answer is yes, there is a solution, I can show it to you and you can check it, then there's a way to translate an example of any such problem into B. Okay? It means that B has some kind of universal expressive power that allows you to encode any problem in A. Let me give you some examples of problems in A. We already talked about, can you visit all these cities? What about, can you color this graph red, blue, and green so that no pairs of vertices that are neighbors are the same color? Here is a bag full of puzzle pieces. I dump that out on the desk. Can you fit these puzzle pieces together into this shape, et cetera, et cetera, et cetera. Okay? So B is NP-complete if any problem like that can be expressed as an example of B. Now, if this was 1936, you'd be saying, my God, how could anything possibly do that? But for better or worse, this is 2017, and you're like, this is not surprising at all. What do you mean? All I have to do is code up a program that checks solutions of A and run it on my phone. And then the general problem B is there any way to get that program on my phone to say yes? Why is this interesting? I hate teaching computer science in 2017. At least you're not checking your phones while I said that. So that was good. Anyway, what I'm trying to say is that these problems exist because of universal computation, which is now part of the air we breathe. And in 1936, the fact that there were computers that could run all these other things and simulate any other computer was like a really big deal. But now, now on your browser on your phone, you might be running a virtual machine which is running something which simulates the Apple II that I had in high school and so on. Okay, so let me give you an example of a concrete NP-complete problem. But I want to point out that as long as you put a polynomial time limit on the running time of a program, we've already kind of said, oh, there's a light bulb there. We've already said an NP-complete problem, namely, here is a program, here is a reasonable time limit on how long you let it run. You can give it any input you want. It either says yes or no. Can you make it say yes? Okay, do you see why that's NP-complete? It's NP-complete by definition because that program could be checking whether the input you give it is a valid Hamiltonian path through a graph or a valid traveling salesperson tour with a total length of less than 10,000 miles or whatever. If a problem is in NP, that means solutions can be checked by a computer program. So see whether you can get that checking program to say yes. That's the same as asking, is there a solution? Yes? Clear? Unclear? Not clear?
Why,
Thank God. What's your question?
why complete with this complete?
Well, it means, what it really means is that, oh, and I forgot to say that B is itself in NP. It's complete because it lies really at the top of NP, and it has this complete power to express any other problem in NP. So, hard means complete or worse. It might be it might be outside NP. So let me give a more concrete example because I think, you know, there isn't hard math today, but there might be hard concepts. Yes.
I just wanted, so is the, for B to be NP-complete, needs to express every
Yes. The claim is that for any A in NP, you can translate from A to B. With a different translation, but yeah. Okay. Yes, exactly. Other NP-complete problems can all be translated into each other, right? Which means that if at 4 this morning you find a polynomial time algorithm for B, for any NP-complete problem, you will have proved something astonishing. You will have proved that P and NP are equal, that they're the same. Because you will have found a polynomial time algorithm that works for any problem in NP. And then, you know, some people will worship you and others will try to assassinate you because, you know, you'll have shown that any problem where solutions can be checked, solutions are also easy to find. Which we don't believe. I mean, that's like saying, here is a big pile of hay. You can check to see if something is a needle in this haystack by poking your finger with it. Therefore, needleness, or having a needle, is checkable. That means now you can find it, no matter how, you know, even in an exponentially large pile of hay. You know, or let's say, do you believe scientific theories are checkable? I've got a great theory. The orbits of the planets are ellipses. Okay, so roughly speaking, we can check that. Well, now you just have some program you can run on your phone that will find these theories. That would be horrible, right? You could also, of course, break every cryptosystem. Who cares? But I mean, what really matters is that we would no longer need, human ingenuity to come up with wonderful new scientific theories. That would be the biggest consequence.
So can you repeat what you said in order to prove that NP? What would you have to do?
Okay, I do want to get to a concrete example very soon because I think then the following will have more force. At the moment, it's not clear that there even is such a problem B. Okay, I made this claim about running programs on your phone, but in 1972, it was like, wait, what could this possibly mean? We know that certain problems can be translated into other problems. How can there be a problem that every problem in NP can be translated into? Okay, so let's pretend that we're not even convinced such a problem exists. But if it does, if B is in P, then A is 2 for every problem in NP. And then, and then P and NP would be the same. Okay. So, good. All right, concrete example. All right. So, partly because you do live in the modern age, you know that one of the sorts of things which can carry out any computation is a Boolean circuit. Because you know that deep inside your phone and your computers, there are Boolean circuits made of transistors where wires carry true and false values, and they go through things that carry out individual logic operations, like that means and that means or, and after a while, out here is some output, okay, after a bunch of layers. So for instance, you know that if you had way too much free time and poor taste in how to spend it, if I asked you, does this graph have a Hamiltonian path, you could laboriously translate the Hamiltonian path checker into a Boolean circuit that has that particular graph hardwired into it, where the inputs correspond to our choice of edges, which supposedly form a path that visits every vertex, a long series of simple logical operations that check that that works, and then finally an output that says true if it does. So the question of does this graph have a Hamiltonian path would become the question, is there any input to this Boolean circuit that causes the output to be yes? Okay? Well, actually, we haven't moved away from the thing I said about your phones before. We're just saying, I'm just reminding you that phones are made out of Boolean circuits that can compute. Now let's try to get away from that a little bit more. So let me introduce you to a problem called 3-SAT. So 3-SAT is a problem which looks like this. I have a bunch of Boolean variables, and I have a bunch of constraints, or clauses, or terms in my Hamiltonian, which might say things like, I demand that x1 is true, or, that's an or x2 is false, or x4 is false. And then there could be another constraint that says, well, I demand that x2 is true, or x17 is false, or blah, blah, blah. And there's a whole bunch of these. And the question of 3-SAT is there a setting of these Boolean variables that simultaneously satisfies all of these constraints? And if you think of this as a sort of spin glass model, in this case involving 3 spin interactions, then imagine you could literally have a Hamiltonian where it's the sum of a bunch of terms, where each term is 0 if that constraint is satisfied, and 1 if that constraint is violated. And then the question is there a zero energy state? Is there an unfrustrated state? I will now reduce this circuit problem to 3-SAT. It's not very hard. First of all, we just add some more variables, which we are perfectly entitled to do. These variables don't have to be these original variables. We can add more. And I'm going to add variables that live on the internal wires of the circuit. So for instance, here I'll add a variable called y. And now what I'm going to do is encode the claim that the circuit functions properly and outputs true into this format. And that's not very hard. It is called SAT, short for satisfiability, because we are trying to tell if this formula is satisfiable. The 3, and thank you for asking, is the number of variables appearing in each clause. Okay. So let me focus on this little gate. This gate, if it works properly, y is the logical and of x1 and x2. In other words, y is true if and only if both of these inputs are true. It is a little exercise from your first year electrical engineering course to write that claim in this format. And it says things like either x1 is false or x2 is false or y is true. And be nice to me and let me have some clauses with fewer than 3 variables. Either x1 is true or y is false, and either x2 is true or y is false. Okay, so now I did your homework for you. You can just check that this triplet of clauses is satisfied if and only if, indeed, y equals the and of x1 and x2, whatever they are. I do this to each gate. I build up this whole list of clauses, and at the end I say, and I want z to be true as well, so that the circuit output's true. Okay, now the question of does the graph have a Hamiltonian path or whatever has been laboriously translated into, is it possible to satisfy this Boolean formula? Okay, so if this has if this has n variables, there are only 2 to the n things to check. Okay, that's exponentially many. Suppose you magically figured out a way to tell, given a Boolean formula, in polynomial time, whether it can be satisfied. That means P equals NP, and you can magically find anything which can be checked. All you have to do is take the checking program, code it in machine language into hardware, and then in this form, and then check to see if you can satisfy the formula. Okay? So unless you believe that everything which can be checked is easy to find, this problem cannot be solved in polynomial time. And indeed, we believe things that are even a bit stronger than that you essentially need some kind of exhaustive search here, that this takes 2 to some constant times n time. Okay, you can certainly be a little clever, but roughly speaking, you're going to have to search the entire tree. All right. Questions so far? Yes?
So you could get better than 2 to that for some nice specific cases, but for the worst case, you'll always be back to that.
There is a small dedicated community of people who try to make the constant here as small as possible. Yeah. And you can be a bit clever by using the structure of the clauses. All right. Okay, by the way, exercise, a somewhat advanced exercise, but you're all very smart and hardworking, which, as you know, is ultimately more important. Prove that 2sat, which means the same problem, but where I only have pairs of variables interacting in each clause and not triplets, prove that 2sat is in P, that it can be solved in polynomial time. Okay? So somehow you need 3, to have 2 inputs and 1 output, or you need some chemistry, right? With A plus B turning into C or something like that for this problem to get hard. Now, I want to emphasize, we don't know this problem is hard. And the whole question of whether P versus NP or not is considered the biggest open problem in theoretical computer science and one of the biggest open problems in all of mathematics. Okay, so we're in the following embarrassing situation. We have literally thousands of problems which are NP-complete. We don't know that any of them are hard. What we do know is that either they're all easy or they're all hard. Okay? And this conditional hardness is the best, really, that we've been able to prove. Okay? Yes?
I want to go back to the picture you drew up. Since the problems inside E are also relatable, does it mean that there is also a subset of E where, again, everything can be translated from either NP P or no, like inside the P?
There are problems that are called P-complete. And these are among the hardest problems in P, just as NP-complete problems are among the hardest in NP. You have to be a little bit careful, though, with your notion of translation. So when we define translation or reduction for NP-completeness, we usually say polynomial time. Here, though, with polynomial time, you could answer the entire question, right? So to get an interesting notion of completeness, as you move down in the hierarchy, you need to be more conservative about what you mean by translation. And so there are even lower complexity classes, like what you can do in logarithmic space and stuff like that, that you could use as your allowed translations for defining P-completeness. But yes, it's a good question.
Also, if I can translate something from NP to a point inside the P, and then translate that like the point on the left, from the point on the left to the right, doesn't mean necessarily that there is a direct translation from the point at the bottom. That second one.
You're asking whether translations can be composed.
Yeah.
Yes, indeed. I've already sort of used that without telling you. All right. So the story I've been telling is first reduce this general question of computer programs to a question about Boolean circuits, then reduce that to a question about 3-sat, and I'll show you one or two more, and I promise that'll be all. So indeed, this is a transitive relationship. So if A can be reduced to B and B can be reduced to C, then A can be reduced to C, the same way you could translate from one language and then to another. And so indeed, the way we prove most problems are NP-complete is by translating to them from some other problem we already knew to be NP-complete, as opposed to going all the way back to the basic question of what will a computer program do. So in order to move a little bit closer to physics, let me quickly give you one or two of those examples. Because the fun thing about these thousands of NP-complete problems is that many of them, it's really not clear when you first hear about them whether they're easy or hard. Okay? So I give you a graph, and on that graph I define an Ising ferromagnet. Okay? What is its ground state energy? Easy or hard? It's easy. Point them all in the same direction. Good. That problem is in P. Now, I make it an antiferromagnet. You might think it's still easy because you're always thinking about square lattices. So sure, just flip all the odd sites. And okay, but it's a graph. It's not a square lattice. Indeed, I agree that if the graph is bipartite, you can flip all of it. But what if it's not a bipartite graph? All right, so there is another problem called max cut, also known as Ising antiferromagnet.
Can I ask a
Yes,
basic question first?
good.
So we're talking about decision problems.
Yes, but if the decision problem is hard, the optimization problem is at least as hard. Because if you can find the optimum, you also know whether the optimum is beyond a certain threshold.
Yeah. But just like more generally, so right, these are decision problems. So that means the solution to any instance is just yes or no, right?
Right.
Okay.
It is typically true that if it's easy to tell whether a solution exists, it's also easy to find it. This is not always true, but it's typically true. So for instance, suppose you were able to tell whether a 3-sat formula is satisfiable or not. Okay? So you have a magic box which says yes or no. What you can do now is try setting individual variables. So notice that this clause, for instance, if I set x1 true, the whole clause would go away. because these are ORs, and any one of these will make it happy. But if I set x1 false, it becomes a shorter clause. Okay? So if you have a magic box which can tell whether a SAT formula is satisfiable or not, you can quickly find a solution by setting one variable at a time. Every time setting the variable the wrong way, the magic box says, no, it's not satisfiable. You said, oh, okay, sorry. I'll set that the other way. And you'll just cruise through all the variables that way, trying each one at most twice, and then you'll have found a solution. So when the decision problem is easy, the search problem is typically also easy. Obviously, I'm using the structure of SAT a bit here when I say that if I set some of the variables, I get another SAT problem on the remaining variables. That's not always true. You have to think about it a bit. So for instance, in a spin glass, if I set a spin of some site, well, you can think of that as an external field on the neighboring sites. So if you have a magic box which tells you the ground state of a spin glass, which is also allowed to have external fields, then you can do this. If for some reason you had a slightly weaker magic box which couldn't handle fields, then you would have to think a little bit more. I still think you could do it, but I would have to think about it. Okay.
So it's actually not at all trivial to say that saying that something's in NP is a statement that you can check the solution.
Oh,
the
but
is just yes or no.
But here's how. Yeah, sorry. Think of it as a conversation. Again, Merlin says this formula is satisfiable.
Right.
Arthur scratches his head and says, "How? I don't see that."
Yeah.
Merlin says, "Here's what you do: set x1 true and x2 false, and blah blah blah," and just shows him the solution. Arthur is capable of plugging that solution in and then saying, oh, you're right, it's satisfiable. So the
right? Just the solution that Merlin gave was inactive, satisfied.
So for me, the nicest way to define NP is to say, if the answer is yes, there is an easily checkable proof of that fact. Now, in this case, if the question is, does a such and such exist, the proof is usually the such and such.
Right. Yeah.
Right? And that's the case for most of the problems that we look at.
Oh.
Yeah.
Whether or not you can come up with the proof.
Right.
Okay.
Right.
Okay, great.
Yes. Good. Okay. Good. So max cut is the following problem. By the way, one thing I'm kind of falling down on, but I think it's okay, is for a computer scientist, you're ultra careful when you define a problem about asking what is the input to the problem, okay? And what is the question about that input which you're asking? You don't just wave your hands and talk about ground states or something. So the input here is a graph. And the question is, can I divide the vertices of the graph into two sets? Well, let's see. You give me a graph G and a target K. That's your threshold. And the question is, can I divide the vertices into two sets with at least K edges crossing in between them? Okay? So we want to know if we can have K or more edges crossing from, say, a black vertex to a white vertex. But this is just the same up to scaling as finding the ground state of energy of an antiferromagnet, right? Because we're trying to maximize the number of edges whose endpoints have opposite spins. Okay? Good. But it's true to make it a decision problem, you give me a number, which I'm trying to achieve. Okay. All right. I'm going to almost prove to you that this is NP-complete. I'm going to do it first by defining a slight variant of SAT, which is called, and I apologize for all these acronyms, it is called NAE 3SAT for not all equal. So this is just a very slightly different constraint satisfaction problem. Instead of clauses which are ors of three things, so this clause will be happy if this is true or that is false, or any combination of two or more of those things. This has clauses that say things like this. It says, I don't want these all to be the same. Okay? So SAT would be unhappy if they're all false, and AESAT is also unhappy if they're all true. In fact, let's not even think about true and false anymore. Let's say they're black and white. Okay? So this is a problem, if you like, where I have interactions between triplets of spins, and the Hamiltonian demands that they're not all +1 and not all -1. Which is, if you think about it, a cute little polynomial in their spins. So you can think of this as a little 3-spin system. Okay. I will not prove to you that this is NP-complete. I will leave that to you as an exercise. See if you can reduce or translate 3SAT to NAE 3SAT. You might think, oh, this is easy, because this is the same as saying x or x1 or x2 or x3 and not x1 or not x2 or not x3. But did I just translate 3SAT to NAE 3SAT? No, I went that way. Okay, I just showed that if this is hard, that's hard. We need to go the other way and show that if this is hard, that's hard. It's a little confusing at first because 3SAT is this fundamentally asymmetric problem which wants things to go in a certain direction. NAE 3SAT is symmetric. So I'm asking you to build asymmetric constraints out of symmetric pieces. You go to the hardware store. You want to make a 3SAT formula, but they're all out of 3SAT clauses. They only have NAE 3SAT clauses. Can you still build what you wanted to build? Well, you might have to go to 4 variables. Luckily, they have a box full of those too. And then maybe you could figure out how to break those up into 3. Okay, it'll be a fun exercise if you choose to do it. If you believe me that this is NP-complete because I can reduce from here to there, I will now reduce from here to there and show that this is NP-complete. It's really easy. In order to express a Boolean problem as a problem about graphs, we need 2 important things: a variable gadget and a constraint gadget. Here is a variable gadget, here's another one, and here's another one. And I can have as many as I like. And how does this variable gadget work? I'm going to set my threshold high enough so that all of these edges need to cross from one set to the other, which means you will be required in any solution to make one of these black or spin up if you like, and the other white or spin down if you like. Okay? I guess since this is a blackboard, white is black. Okay. Those are the variable gadgets, and each one sort of encodes 1 bit worth of choice. Okay? Now I need the constraint gadgets. A triangle. And I'm going to set my threshold high enough so that 2 out of 3 of the edges of this triangle need to have opposite spins at its endpoints. And now, anytime I want to translate the constraint, for instance, that these 3 are not the same, I connect it to those. And for instance, now you see, let's see, what else do I do? I also set my threshold high enough so that all of these edges need to have opposite spins. And now you can see that except for this edge, both of these edges have opposite spins. So what do I do in the end? If I have an NAE SAT formula with n variables and m clauses or constraints, I set k to be equal to n plus 5m. And if you think about it, the only way to achieve this is to have all of these edges have opposite ends, and all of the edges connecting to each of my constraints, and 2 out of the 3 edges within each constraint gadget. So if you are interested in antiferromagnet, just do the obvious scaling between the energy and the number of edges with opposite sides, and then the question of can you get is there a state with an energy below a certain threshold, can be a translation of this, which is a translation of lat, which is a translation of anything in NP. Okay? And it's not even a spin glass, it's just an antiferromagnet.
Is there about the constant phi? Where does that come from?
It came from this gadget. It's not a deep constant. It's not, I mean, I would say that 1970s and 1980s theoretical computer science consisted largely of doodling. Okay, you want to prove something's NP-complete, you doodle a gadget like this. And then you figure out, if there's a threshold that needs to be set, you figure out how to set the threshold. The point is simply, and obviously, look, there's a triangle, so this is not bipartite, right? So, of course, this can be effectively a spin glass in general. All right. So, since I have only 3 hours left before lunch, let me wrap up a little bit. So there's this whole branching tree of NP-complete problems. Not only do they include things about these discrete math and graphy things, they have some real surprises. Like here's a problem for you. The input I give you is n integers a1 da 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 an, and let's say these integers themselves can have n digits each, and then the question is this integral a2 theta, is this integral non-zero? That problem is NP-complete. It's not clear, by the way, that it's in NP, but it is. That's kind of fun. I mean, it means that symbolic integration is hard sometimes. And it means that numerical integration probably sometimes requires an exponentially large number of sample points. And since I told you that these could be n-digit integers, actually, the point is the integrand can oscillate very quickly. Okay? So there are lots of surprises there, but now let's just pull back for a second. So we've already talked about how there's a big cultural difference here between computer science and a lot of other fields in this focus on worst case, okay? So, I mean, the story we're telling is that this problem of finding the ground state energy of an antiferromagnet is sometimes hard because sometimes the graph that the antiferromagnet is defined on has been diabolically designed to encode some complicated computational question. Okay? Designed by that adversary, the word adversary that I erased before. And of course, this is not the setting that most sciences find themselves in. Now, there are a couple things we could say about this. One is that, you know, the old-fashioned thing to say would be, well, at least it's important for you to know that there's no algorithm which will always work, even if it works on everything that you've ever tried it on, ever. Okay, all right, so that's one answer. You know, another answer is that it's an existence proof that the problem can be hard. And for instance, you know that for an antiferromagnet on a graph that has odd loops that is not bipartite, you know that it can be pretty bumpy, its landscape. I'm not going to say glassy, but it could be glassy. Can it be glassy? It could be glassy. Yeah, maybe. All right, okay. It could be spin glassy, maybe. So that's good. The other thing to know, though, is that since 1990 or so, it's actually not fashionable anymore in computer science to prove that things are NP-complete. It's considered a little too easy. You know, people still do it occasionally. There's still the occasional surprise. But it's now regarded as the beginning of the story and not the end. Okay? So the question then is, well, first of all, even if we stick with worst case inputs, which might be diabolically designed, you could ask, even if we can't, for instance, find the optimum, can we have an approximation algorithm which is guaranteed to get within 80% of the optimum, for instance? Okay, so that's one type of question. And it turns out here that different NP-complete questions are different. So this picture says, oh, they can all be translated into each other, so they're all equally hard. Well, once you start talking about approximation, then there are some which can be approximated arbitrarily closely within a factor of 1 minus epsilon, where the running time grows as a function, it grows as epsilon goes to 0, but you can get as close as you want to the optimum within polynomial time. Maybe as you get closer and closer, maybe the exponent in the polynomial has to go up. Maybe it's just a prefactor. At the other extreme, there are NP-complete problems where even getting within any constant of the optimum is just as hard as finding the optimum, meaning that even getting within, say, a factor of 2 or 1/2 would if you could do that within polynomial time, then P and NP would be the same. Okay, and there are things in between where we think you can get, there are a bunch of problems where we think you can get this constant in polynomial time, but no better. Okay, and in fact, for this max cut problem, we believe the constant is 0.878. It's kind of interesting. You know, there is a polynomial time algorithm which will find an arrangement with at least 87% of the optimum number, whatever it is. But we don't think in general you can do better than that unless P equals NP. All right, so that's one flavor of question. But another flavor of question, which is closer to the subject of this school, is moving away from worst case inputs entirely and asking some question about inputs which are typical or in some sense or random. And you know, that leads us to random Boolean formulas, random graphs, and then we can look for things like phase transitions. But I do want to close with one thing. You might think that the worst case hardness of a problem could be basically ignored if you think that the hard cases are very rare. Okay? So for instance, there is a problem called linear programming, which if you've ever read an economics textbook, you know that chocolate chips cost a certain amount per pound and dough costs a certain amount, and you can sell the wheat cookies for $2 you want to maximize your profit within your budget. Okay, all right. So you have a set of linear constraints, and they form a high-dimensional jewel, and you want to climb to the top of the jewel. Okay, that's the linear programming problem. Okay. So there is an algorithm, which is a very simple greedy algorithm, which goes back to, I forget, the 60s, called the simplex algorithm, where you start at any solution and you just climb up this jewel formed by all these, this polytope whose facets are the constraints. And in practice, this always works really fast, and everybody uses it. So some clever people working for the adversary came up with a weird example where it leads this simplex algorithm to make an exponentially long series of tiny improvements until it finally gets to the optimum. And they said, ha-ha, there are times when the simplex algorithm takes exponential time, and most people paid no attention because that never happens. So there is a field called smoothed analysis, and I really am almost done, where you take any problem, including one designed by the adversary, and add a little noise. Just tweak things a little bit. And for the linear programming problem, it turns out, and this is due to Shenghua Teng and Dan Spielman, that with probability 1, even if you let the adversary design a problem, if you perturb the coefficients of the constraints a little bit, then with probability 1, it becomes easy and the simplex algorithm solves it very quickly. So that's a very satisfying explanation for why the simplex algorithm works quickly in practice. The hard examples are rare, they're fragile, tweak them even a little bit, they get easy. But we do also believe that there are NP-complete problems where hard examples are common and even generic. So for instance, in cryptography, you do not want a cryptosystem where I say, you should buy my cryptosystem because there exist messages you can send your friend that an eavesdropper will not be able to decrypt. That would not be satisfying. You want all or almost all of the messages to be hard to decrypt. And so in the next few lectures, we'll talk, for instance, about random constraint satisfaction problems, random graph coloring, or random satisfiability problems where we think that there is a whole zone of hardness where generically random problems in that region are hard to solve. Okay, thank you. Questions over lunch? Oh, yes, question? You're standing in between them and lunch, just so you know. What's your question?
Does this overlap with Shannon theory? Because it kind of smacks of Shannon theory, like finding a set which is sort of typical and some measure.
We can talk about that more. I mean, Shannon is really more about information, and this is more about doing complicated things that process that information. So I don't immediately see a connection, but we could talk. Yeah. Yes?
I don't have a feeling. It seems very difficult to prove that something NP-complete, because then you have to show that every NP problem is reducible, or not reducible, but in the sense that B is bigger than A.
Well, no, because the idea was if you believe that Boolean circuits can carry out any program, then you already know that the general question of asking whether a Boolean circuit can ever say yes is NP-complete. And then we've translated that into the general question of can an antiferromagnet on a graph have energy below a certain point? And it would be very laborious, but you could take any Boolean circuit you wanted, which is checking any property you want in any example you want, and eventually convert it into a graph and ask this completely concrete question there, is the ground state energy less than blah, blah, blah? So, I mean, my proofs here were sort of proofs by example. I only drew something representing one constraint.
Well, you have to come up with
In general, there'd be many, but once you know how to encode a variable and a set of constraints, if you already knew that that constraint satisfaction problem was NP-complete, you know that your new problem, where you've been able to express those variables and constraints, is also NP-complete. Any other questions before lunch? Okay, great.